Okay, good afternoon. Let's start now. So this is the last lecture. We are going to have exam. Oh, there's no outline. On Thursday, right? You can bring one cheat sheet only, two-sided. Okay. Because I want you to rewrite what you have learned before and take this opportunity to do something. So today we don't have article of the days. I saw a video from the Facebook, pretty good, and I try to share with the undergraduate student. It's more useful for them, but I think it's also good for you guys. Although you guys are much more hardworking and know what you are trying to do, but I think it's still good to share with you 4 minutes video. But then there's no sound. It's very bad. Let me try another one. It was from my computer. I tried to project it there. This one? One more time.
Beauty parlor, and I was flunking out of college at a 1.7 grade point average. I hope none of you can relate. At a 1.7 grade point average, I was sitting in my mother's beauty shop. They still call it beauty shops now, what they call it now? Yeah, and I was sitting in a beauty parlor. I was sitting in my mother's beauty parlor, and I'm looking in the mirror, and I see behind me this woman under the dryer. And every time she looked up, every time I looked up, she was looking at me, just looking me in the eye. I didn't know who she was, and I said, she said, somebody give me a pen. Give me a pencil. I have a prophecy. March 27, 1975. She said, boy, you are going to travel the world and speak to millions of people. Now, mind you, I flunked out of college. I'm thinking about joining the army. I didn't know what I was going to do, and she's telling me I'm going to travel the world and speak to millions of people. Well, I have traveled the world, and I have spoke to millions of people. But that's not the most important thing, the success that I had. The most important thing is that what she taught me and what she told me that day has stayed with me since. I've been protected. I've been directed. I've been corrected. Fail big. That's right. Fail big. You only live once. So do what you feel passionate about. Take chances professionally. Don't be afraid to fail. There's an old IQ test was 9 dots, and you had to draw 5 lines with a pencil within these 9 dots. without lifting the pencil. The only way to do it was to go outside the box. So don't be afraid to go outside the box. Don't be afraid to think outside the box. Don't be afraid to fail big, to dream big. But remember, dreams without goals are just dreams. And they ultimately fuel disappointment. So have dreams, but have goals. Life goals, yearly goals, monthly goals, daily goals. I try to give myself a goal every day. And understand that to achieve these goals, you must apply discipline and consistency. You have to work at it every day. You have to plan every day. You heard the saying, we don't plan to fail, we fail to plan. Hard work works. Working really hard is what successful people do. And in this text, tweet, twerk world that you've grown up in, remember, just because you're doing a lot more doesn't mean you're getting a lot more done. Remember that. Just because you're doing a lot more doesn't mean you're getting a lot more done. Don't confuse movement with progress. My mother told me, she said, yeah, because you can run in place all the time and never get anywhere. So continue to strive, continue to have goals, continue to progress. And anything you want good, you can have. So claim it. Work hard to get it. When you get it, reach back. Pull someone else up. Each one, teach one. Don't just aspire to make a living. Aspire to make a difference.
Right, that's it. So I like to share, I really like this video, and I think it's good for the undergrad. I'm sure many of you already doing what he's talking about, right? Especially for some of the foreign students. The reason you are here, you really know what you want, right? You have goal, right? But still, I was also a foreign student, but then I lost my goal eventually. There was a period that I really got lost. So I hope that in the future you don't have this problem, right? You guys are still young, so try to remember this, okay? So we have went through a whole semester, right? We learned the basics. The most important is we want to improve the quality matrix of our design, digital logic. Remember what are they? PPAC, performance, power, area, and cost, right? If you can make a best optimization for that, you don't need to learn anything of this. We learn this because we want to improve the PPAC. Right? We learn about the fabrication process, the basic transistor and diode model, a lot of equations. Again, I said, you probably don't need this anymore in the future, right? But you learn this because it helps you to appreciate the model we are going to develop in the circuit, right? We learn about wire model, and then we start with the inverter, combinational logic, right? And then arithmetic building blocks, right? And eventually we went to sequential logic and interconnect issue, timing issue, and memory. Okay, and then we are going to have exam on Thursday. Right? Make sure this time is correct. Okay. Now today we are going to have a review. There are many slides here. I try to put here just for your information that I feel these are more important. If you don't have time, at least you should understand what are in this review slide, right? But in principle, everything is covered in the lecture. Okay. I will also go through some examples, but I don't know how much time we have. Right. So the first thing I will start with the most recent one. Okay. How do we size a buffer chain? Right. We learn about logical effort, or learn about all this minimizing the delay. Right. But if we try to drive a very large capacitor by using a small one, For example, our intrinsic delay may be 2.5 femtofarad. The off-chip load may be 20 picofarad, right? This is very large. How do we size it to minimize the delay, right? We want to put it as an inverter train like this, right? So remember what is the best way to size it? You want each stage to share the same amount of delay, correct? Right? This is the intuition you need to have. Each stage is share the same amount of delay, right? So how do we do that? So we have some equation. First of all, we need to find out what is the total fan out, right? Total fan out is the load divided by the intrinsic delay. The first one, not intrinsic, I mean. So sorry, this is really a typo. The intrinsic cap, not delay. Cap, right? The input cap to the first inverter. Okay, and then we assume gamma equal to 1. This is given, right? With gamma equal to 1, the best fan out is equal to 4, right? 4, what does it mean? It will go by 1, 4, 16. You keep increasing the size of the inverter, right? And eventually you can drive it, correct? Right? And then based on this, then how do we find the number of stage that we want? You should be very familiar with this now, right? It is written here, right? Because this is the total fan out, then and each stage we say we want to make them even, right? So it will be F to the power n equal to the total F, right? And then we just take the log, then you will get this one. Any question about this? How to find the number of stages for the minimal delay? Any questions? Now, if you don't have question, now the problem is once you fix this to be 7, then the fan out won't be 4 anymore, right? So you need to redo the fan out, right? Because if I fix this to be 7, I need to have 8,000, the capital F to the power 1 over 7 equal to something, right? And which is 3.6 in this case, no longer 4. And that's how you size your transistor, right? For example, if my first transistor has a width equal to 1 micron, then what is the width of the second stage? So we are talking about the effective width equal to 1. Then the second stage has to be what? Say again? 3.6, thank you. Right, and then you keep increasing it. This one will be 3.6 squared, right? And you just keep going until you have 7 stages, which is 3.6 to the power 6, and which consume a lot of area. But this one gives you the minimal delay. What is the delay of this circuit? Total delay of this circuit. Say again. NTP naught times 1 plus F divided by gamma. Okay, so any question about this? I already wrote the equation here, right? And this is, of course, just equal to 1 plus F divided by gamma, right? What is N? 7, right? Gamma is 1, and F? 3.6, right? F is no longer 4, okay? It's 3.6. Okay? And TP0 is going to be given to you, maybe, or you have to find out yourself, right? Any question about this? So this is a very important when we try to minimize the delay, but then it tells us that we actually have a very large area, right? But very often we don't need that. We will start with what? We will say, actually, for the off-state, off-chip loading, we don't need gigahertz of operating frequency. Maybe they just request hundreds of nanosecond delay, right? So you will be given saying that, okay, my delay may be, I just want it to be 10 nanosecond, right? So my intrinsic delay is 100 picosecond. So what is the ratio between T and TP0? 100, right? The requirement is that you need 100 times larger TP of TP0 delay, right? And you have to solve this equation. But usually you can look at the plot. This plot, how do you read it? It's just telling you how you put the number of stages on your train, right? If you have more stages, then you have slower delay. And the delay is expressed as the propagation delay divided by the intrinsic delay. How many times of the intrinsic delay, right? So as an example, if I say, hey, I want my intrinsic delay is 100 picosecond, and the requirement is to drive the offload by 10 nanosecond speed, then I want this TP over TP0 at least less than 100, right? So this is, then I have to pick it. Of course, then you have to pick up what is the F. For different F, I have different curve. For example, if F equal to 10,000, this is one stage, it is going to have 10,000 unit of delay. Then if I can make it two stages, it becomes, how do you read this? This is 100, this is what? 200. This is a log scale, right? 200 unit of delay. If I can make it three stages, then it is less than 100 unit of delay. So I will design a buffer so that I have 3 stages. That is good enough. I don't need to design 6 stages, 7 stages. Okay? So by just using 3 stages, then I will be able to achieve the specification. Okay? So this is the setting, the scenario. Okay? Any question about this?
Are you going to give us this one?
If I'm going to ask you to solve it, yes, I will give you this one, right? Because this equation is difficult to solve. You need to solve graphically, which I don't want you to spend time on. No question? Right, and then with this, then we say, hey, now I can try to find out what is total area and power consumption of my buffer train, right? Now we're talking about buffer, right? So each of them has an A mean. What is A mean? The layout area of the smallest inverter, right? And then you see that the first stage is A mean. The second one will be F times A mean, right? The third one will be F squared. And the last one will be Fn minus 1, right? And in our case, the first case, this is 7 minus 1, right? Very large. But we just add them together. This is just geometric mean, sum of geometric mean, right? H is just equal to this one. Okay? And for the power consumption, we know it is just equal to, this is not clear, this is C mean V squared. Okay? The minimum CV squared is the power consumption of the minimum size inverter. If you have larger capacitor, you will have more consumption, right? So each stage also scale with F. Okay? And then again, you use this geometric mean, and then eventually you will get this one. Okay? And what is this part? This is talking about the power consumption due to this extra inverter train. Okay? Any questions? Right. But I mean, there are many equations, but after all, after this class, after exam, what you need to take home is that you have different scaling for minimum delay and also for meeting the specification. It's a trade-off, okay? And you know how to calculate the area.
So are you going to specify in the question if we are going to solve it based on the requirement or based on the...
Yes, definitely I will ask you to do so if there's such a question. Yeah. So this one, I will just skip. I just have a more detailed example. Try to look into this to understand how to do it. Okay.
So you're going to give the right side graph?
This graph?
Yeah.
Yeah, if I want you to use the graph, I will give you. Don't worry. So what I'm saying is that you don't need to memorize this equation. Right? You can put into cheat sheet, but I don't expect you to solve it. Okay, so this is about the interconnect. how to drive large capacitor. We were talking about clock, right? And also off-chip loading. And then for SRAM, right? We learned SRAM is something important, very important nowadays. Again, our goal is to optimize the area, the robustness, the leakage, the speed, and the yield, right? PAC. Again, power, performance, area, and cost. Remember this word. This is very important. Right. So how do we store the data? Right. The basic thing, you really need to know the basics, right? Maybe we store 0 here, and then because this is an inverter, this one is going to drive another inverter. So what is the node here? 1, right? Which is VDD. 1. Right. That's how we store the signal. It's a cross-coupled regenerative logic, right? So very stable, right? And that's why nowadays we can scale to very small size, very low power supply, and it still works and in your CPU. What is Q5 and Q6? Why do we need these two transistors? You really don't know? Huh? Access transistor. Yeah. So if this is off, right? If this is 0, the word line, this is called word line. If it is 0, then this is off. Then you cannot access it, right? Why do we need to access it? Because we have many transistors in the array. We need to adjust them individually to read or write. Okay? And this is called bit 9 and bit 9 bar. That's how SRAM operates, right? Now, this is how you store the data. But how do we read the data? How do we read the data? First of all, you need to understand how you read qualitatively, right? So when we read the data, what we do is we will pre-charge the bit 9 bar and bit 9 to what? 1 or VDD, yeah? So you see that both of them are at VDD. And then we are going to turn on this access transistor, right? And the goal is that if this is 0, it's going to pull down the voltage here, discharge it. If this is 1, what will happen to this node? If this is 1, what happens? Nothing happens. It's still at VDD at the beginning, correct? Yeah. But we are reading the cell. It's important not to disturb the cell. You will always hear about cell disturbance during read, right? If you work in the memory industry, people would. This is a matrix they care about. So the goal is that I want this node to stay high or low when I read this cell. I'm trying to read this cell. Nothing happened here. Both are 1. This is 1. This is original at 0. Once I turn it on, what happened to this node? Is it still at 0? You say it becomes 1. If it becomes 1, is this still stable, the data? If from 0 to 1. You flip the data already, right? You damage the data. This is not what we want. But that is a good point. It can become 1, right? But we don't want it to become 1. We want it to stay as low as possible to 0. The best is that it is still at 0. The goal is that I want to discharge this node only, right? So it means that from this point to this point, we have a potential divider effect, right? Because you have a resistor here, and then you have another resistor here. Right? So how do you find out what the voltage it will reach for this point? How do you find out the value?
VDD on resistance of Q1 divided by Q1 plus Q5 on resistance.
Very good. He said that this node is going to be VDD divided by R1 times R1, VDD times R1 divided by R5 plus R1 times VY. Correct? Agree? Because of the potential divider effect, right? But we are not satisfied with this step. We want to be more accurate because we don't know what is R1 and R5. We don't want just to approximate it. So what should we do? We just model the transistor equation.
Size in Q1 is greater than Q5.
That is the risk. We'll talk about this later. But how do we solve the Vx?
Vx should be smaller than Vn.
No, how do we solve now this is very important, right? How do we solve Vx? I'm asking, how do you find out the voltage of this guy? Huh? Current equation, can you be more explicit? The current through the Q5 equals to the current through the Q1, correct? And that's what I'm doing here. The current through the Q5 equals the current through the Q1. But you need to find out which equation to use, right? So as I said, we want the delta V to be small. Now can you tell me what is the operation regime for Q1? Think carefully. Linearly, why? VDS is almost equal to 0. Right? So you all know this. And don't get stuck or don't fail just because of you didn't put the right voltage to the terminal. Okay? And let me forward a little bit. This is the equation we have been discussing since the very beginning, right? You want to know this equation, right? If you don't have a space, you should get rid of everything else. At least you should have this one, right? That you know that when the V mean, which is the VDS is the smallest, it becomes the linear mode. Okay, so when VDS is small, you are in the linear regime. Correct? So Q1 is in linear regime. That's what I put here. W on LK N dash, VDD minus VT, delta V minus delta V squared. Delta V is this one, very small. Is that clear? Feel free to ask questions. Now is the time you really need to understand. Don't wait for later.
So we said like BL is the BL bar is the inversion of the BL, right?
Yeah.
Then actually if the BL is going to be VDD, how come the BL bar also can be VDD? It's supposed to be 0, right?
Okay. So this is the name of the line only. Okay. If you try to just the name.
Okay, they
but
don't have any relation.
No relation in this case because we are reading. Okay. If you are writing, you will make them inversion of each other. Right? But we are reading, the only way we can read is pre-charge both of them to very high. And then let one of them discharge and we compare the value. Yeah, so this is a very good question, right? Just because we pre-charge it to 5 volt, that's why, VDD. That's why it is high. Right? So don't get confused. But when we are writing, they have to be complementary to each other. Okay? So this is for the Q1. Then how about for Q5? Which mode of operation is this? Saturation, right? Because this is not PMOS, so don't mess up with inverter. We're using the same skill when we solve for VM for inverter, right? But this is NMOS. And this side is at VDD. This side is at very low delta V, right? And this is VDD. So we have a VGS here. So you are in saturation. Is that clear? And then, so here we don't know, right? So I did not tell you. So I just assume it's due to velocity saturation. That's how I put the equation here. Yeah. So I will give you enough information if that's the case. Right? Yeah. Or if I don't give you, any result will be correct, any answer, as long as you say that. Okay. So that's why we use the saturation current, right? And then we equate them. Then we will be able to solve for delta V. Okay. Now go back to the result. Which one needs to be stronger to be stable? I mean, yeah, which one should be more resistive or more conductive? Someone say Q1 has to be more conductive. Do you agree? Yeah. So whenever you have problem with this, you can do extreme case. Q1 more conductive. Let's think about, let's just make the resistance equal to 0. Superconductive. Then what will be the output here? 0. Is that what we want for this node? Yeah, right? Because we don't want to disturb the content. Okay? Or on the other hand, you can think, maybe Q5 need to be more conductive. Just think of it is very conductive, so resistance is 0. So this one will become VDD. That is not what we want because you flip the content of the cell already. Okay? So there are many ways to think about that, but try to cross-check from different perspectives. That's how you read it.
So when we say more conductive, then that's supposed to be in saturation, right? The other one's supposed to be linear, right? Otherwise, like it would be like the Q5 becomes.
You are saying that this one, because delta V is almost 0, so this is not conductive enough, right? You're right. So then it is going to pull up the delta V until it's conductive enough. Then how can we keep the delta V small? How can I make this term big without increasing delta V? How can I make this term bigger without increasing delta V? Increase the what? VDD, we cannot change it. What can we do?
W by S.
Yeah, so make it larger. So it means we need to make Q1 larger than Q5. Okay, make it stronger. Okay, so this is something you need to take home. Q1 stronger than Q5. Yeah.
In that equation, how did it came to be VDD minus VD?
So here I redrawn the circuit here, Q5 and Q1, right? So this is very confusing, very difficult to work with, right? You need to redraw it. Now I just look at Q1. This is ground, this is VDD, so I put VDD. And here is the drain of Q1, I put delta V. And then Q5, I have VDD, and then VDD to the drain, because this is the B9 bar, right? You're okay with this circuit, everyone? And then you just apply the equation. What is this one? When I put here, what I'm putting is VGS minus VTH. This is what I put here. So what is VGS? VG is VDD. What is VS? Delta V. So that's why I have VDD minus delta V. And then minus VTH. That's how I do it. I cannot see it immediately. It's confusing. So I just do it step by step. Okay? This time you have plenty of time in your exam, right? So don't rush step by step. Okay? Don't just think that, this is VDD minus VTH. No, think carefully. It's VGS minus VT. Okay?
The gate for Q1 is
The gate for Q1, no, is VDD. This is VDD. This is the gate. Because you are taking the output of this one to here. This is 1, and then you apply to Q1. Yeah? Yeah, so same, you need to draw this figure first. If I were you, and I'm not very confident, I will draw this first. And then draw this, I know which one is off. And then draw this. That may spare me 4 minutes, but be guaranteed I will be very successful in the rest of the question. Okay? Step by step.
So the 0 and 1 will be keep altering, right? So
No.
because the inverters are connected back to back, right? So
And
like,
but it's stable. If this is 1, output is 0. If this 0, output is 1.
yeah, but it will be like keep changing, right? Because
It
they
won't
are
keep
connected.
changing. See again, this is 1, the gate is 1. What is the output?
0,
0. When this is 0, what is the output?
1.
1. I did not change anything, right?
Okay. Yeah.
It will just be very stable. Yeah.
And how that delta V
How what? Say again?
delta V
Delta V is just
in
saying
the second after
this one. Oh. What equation should I use? It should be VGS minus VT times VDS. This is in linear mode. Right? If you use the right equation, you get it's linear because delta V is very small. Because we want it to be small. This is just VDS. Okay? Okay, let me move forward. Now, how about right operation? We did not spend time to derive it, right? But when we do the right now, it is complementary to each other. When we write it, for example, now we store 0 here, and we have 1 here, right? And then I try to write 1 to this guy, right? And remember that I don't care about this part. Why? I don't look at this part when I study the right. What's our goal if I want to make this one equal to VDD? I need to bring this node to very high. How can I bring this node to very high? Again, this is just a potential divider, right? How can I bring this node to very high?
Make Q5 more conductive, and it will contradict with the read mode.
Right.
That's why
Make
we
Q,
use that one.
make Q5 more conductive, right? Because again, I want Q5 to be conductive. Extreme case, Q5 has 0 resistance. Then this will be VDD. Then I switch it successfully this time. Correct? So I don't want that because last time I said I want Q1 to be more conductive to Q5 for read operation margin. So if I want to size Q5 to be larger than Q1, then I lose the operation margin, the read margin, right? So what do? We will just look at this side instead. And at this side, Q2 is off, right? Again, I will draw this circuit, put the number there, turn something on, turn something off, right? And I have this circuit. And then I look at this circuit. What do you see? You see a PMOS in series with an NMOS, right? And now what is my goal? What do I want to do with this node? It was 1. What is my goal for this write operation? Write 0. Write 0 means I want to make this guy to be 0. But how do I make this guy to be 0? It's going to be very difficult, right? Because this VDD is competing with this 0. I need to make this one very, very conductive, right? But do I need to bring this all the way to 0? No. This one feed back to Q1. Right? In some case, we say, as long as I can bring this one to lower than VTH, that will be okay. I will turn this off. Right? So last time I have a typo here. This should be smaller than Vx smaller than VTH Q1. Okay? Once I bring this Vx to be lower than the Q1, VTH, Q1 will be what? Off. Once this is off, you see, no one is pulling this 0 anymore. This one will just charge up this guy all the way to VDD. And when this is VDD, then you will just flip my inverter, and it becomes 0. And just regenerate it. Okay? Any questions? Yeah. You need to write a similar equation so that you know how to size it to bring the VTH to be lower than VTH. Vx to be lower than VTH. Yeah.
So basically we need to write a PMOS saturation equation and NMOS linear equation.
Write a PMOS saturation equation, linear equation. Yes.
You said Q3 and Q4 are the same size, and then Q1 and Q2 are the same size?
Yes, which make it symmetric, yes. So Q3 equal Q4, Q1 equal Q2, Q5 equal Q6. Okay. There's a normal way, that's the regular way of designing an SRAM. But maybe you can find some reason to make them different. In some case, I don't know, for some special application that you save area. But this one, I don't know. Any questions? No, it's just because we want to write 0 to this side, so I put this 0. And this has to be VDD then, okay? Because they are complementary to each other. If I want to write these cells to VDD, to 1, then I need to put VDD here and 0 here. But turn out that this is already VDD, so there's no problem. No, nothing happened, right?
So here we are writing 0 to 1, right? So if it is 1 to 0, we need to write there. So then
0
actually,
to 1.
So yeah, right now what we discussed is 0 to 1, right? In case we need to write 1 to 0.
1 to 0, then you look at this side. This side will become 1, this one will become 0, and this is 1.
But that is for read operation, right? That's what we said, like VL bar is like for the...
No, read, both of them are for read and write. When you read it, both pre-charge the VDD.
Okay.
When you write it, just put 1, 0 or 0, 1.
Okay, just a complement.
Yeah.
Okay. So in that case, like always, maybe the like if that is going to be VL bar is going to be 0, then actually like we will have a different transistor operation condition we might be getting there, right?
It won't say, so let's just go over this, right? Let's say now we actually we have 1 here and 0 here, right? And then our goal is to overwrite this one. Then you actually need to put 0 here and 1 here, correct? Because my 1 is here, 0 here. I want to overwrite it. It means this is 0, this is 1, right? And then now the goal is that we go back to, now we need to look at this branch. This is 0. And then, but then the whole transistor got flipped because this is on, this is off, right?
That's
then
what
you just, then you go back to the same
Flips.
equation. Yeah.
It's flips, right?
Yeah, split. So you go back to the same equation. Okay.
Then why we wrote this as a write operation and that one as read operation, because they both can happen simultaneously, right?
You mean when we are writing, we can read at the same time?
Yeah.
In principle, you can do that. In principle, because you will see some change. But let's go to here. The reason is that how we read it, reading is not easy. We actually want to be fast. We read it and we actually pre-charge it and see how the voltage change in this 2-bit line and then go to the sense amplifier. So we are relying on a small difference to decide what is the cell reading. We don't really wait until this is discharged to 0 or 1 because that spends a lot of time. Right? So in this case, you are not able to read and write at the same time. Yeah? But if you say, I have some mechanism that I'm able to detect the change reliably, then you can do that. But this is very difficult. It's not impossible, but you want to have a very good noise margin and over all the cells. So that's why they have this scheme of reading and writing. Okay, so this is the reading operation. And then we talk about the static noise margin, the butterfly curve. Remember, we have two coupling inverter for SRAM cell, right? And we say that what is the maximum noise that you can afford is to draw a square in this butterfly curve. And the one with the larger square, the psi, with which the psi is the static noise margin. Okay, any question about this?
So what about this V node A? So like yeah, that square makes it the noise margin for the node B, right? So the same way like for the node A noise margin, like we should consider the bottom butterfly or like.
Noise margin is talking about the noise margin of the whole cell. We are not doing this individually. And the way to test it is to add two identical noise margin at these two nodes. This is telling us that if I have a noise larger than this amount, then my transistor will have problem. Yeah, but I put it at the same time. Okay, but of course one of these curve, this dotted line, is because of A, and then another, this is because of B, right? And then you just couple it together.
So in this one, the noise margin is the green one or the red one? Because
right.
The red one is the small one. Right?
So the green, so here I skip a little bit stuff. For the dotted line is the noise margin at static situation. You are not reading, you are not writing. And that's the noise margin of your cell, or of your cell. So you have a larger one. But then if you're trying to read it, the noise margin is the smallest. The butterfly curve becomes this. The solid line. And then you have the red one. It becomes smaller. Okay? And noise margin is saying that what if I have a two noise suddenly comes into my cell? It is going to flip my cell or change the data. Okay. Any questions? Okay, then we talk about the timing, right? What is a latch? This is very important, right? The difference between latch and register. Latch, you don't have, sorry, both of them are latch. You don't have a triangle here. And what it does is that whenever you are high, you will pass the data from D to Q, right? For negative latch, wherever it's low, then you will pass the data. And that's why I call it transparent high for positive latch, transparent low for negative latch. When the clock is low, it's just transparent, like a wire going through. Any questions?
This part of the diagram. The one and the arrow below it? Yeah.
What was that?
Like what's happening?
Right, what's happening? Yeah, this is also important. I have data keep coming in, right? It will just copy directly. And here it's just that this is the last data I copy. Once I latch go to 0, then I will just keep this one here.
Shouldn't it be like once the one is back to 0? I'm just asking like why is that transfer? Like,
There's some delay, right?
Oh, because of delay.
Yeah, I think that's what the textbook put. They put this one.
Yeah.
I actually prefer to shift everything,
Yeah,
but I
that's
think
what
this
my
is
question
because
was.
of delay.
Because of delay.
Yeah.
Okay.
And then what's the difference between latch and register? Register is that it copy when you change the level from 0 to 1, right? Or from 1 to 0. Okay, this one is important, right? Now, and then we learn about the timing definition, right? For timing definition, the first is the setup time. What is setup time? It's the time before which your data has to be stable when the clock comes in, right? So I have a register. This is a register, but the same concept apply to latch. It's just all about when my valid clock comes in, you have to be stable. Okay? So when it comes in, here is the clock, right? It goes up. The data has to be stable before it. Okay? If you are not stable, you are going to have the wrong result. And another thing is the hold time. Hold time is that even I already goes up, you need to be stable for some other time. This may due to overlap or due to the special treatment, special architecture of a register, right? Any question about setup and hold time? And then we try to find out what this propagation delay is going to change the way we clock our register, right? We cannot clock it for infinitely fast because we need the data to propagate. So for example, here, when the clock comes up, I will go to copy the data to Q. So, or I should say, the Q, it takes some time for the Q to be valid. And what is this delay? TCQ, right? The cross goes up, then it will be valid here. And then it's going to go through the combinational logic, have a delay. And then it will come here. Can I clock it immediately? Well, when can I clock it? After setup time, right? I need to be valid for a certain time. So the next clock the period has to be larger than the TCQ, clock to Q, propagation delay of the logic, and then the setup time. That determines your maximum frequency, right? Like this. But this is not enough. There's another problem. When I go up, right, then it is going to propagate, right? What if it propagates very fast, like the speed of light? Then it is going to change my data, right? For certain register, we may have some hold time. We say you have to wait for 2 nanoseconds, right? After I copy it. Then you may overwrite it. So the hold time has to be smaller than the delay through the register, and also this one. But this delay is called contamination delay. This is the best case delay instead of the worst case delay. And that determines the whole time is given, but that determines how you should design your circuit, right? And we talk about C-square MOS will overlap. I won't go into details, right? Now, then, those are ideal case. We already discussed. Let me just skip this. But you might have cross skew. Cross skew, what does it mean? You have two registers. This clock does not arrive at the same time, okay? And what is a positive cross skew? Clock 2 arrive after clock 1, positive skew, just by definition, okay? Because the data is going in this direction. What is a negative skew? Clock 1 arrive later than clock 2, right? And although they are positive or negative, but they are all just a number. When I say what is the maximum negative skew, right, then you will become, it's still a positive number, but we're talking about this one arrive later, okay? So how is it going to affect the clock and the timing? Just because this is shifted, the clock 2 is shifted to the right. What is the skew here? What's the value of the skew? Delta, right? It's shifted by delta, right? And because shifted by delta, I'm not going to read it at 3, right? I'm going to read it at 4. So actually I have more time. I can reduce the period for positive skew. Right? And similarly for hold time, now it is different. We actually, because you are doing it later, then I have more time to propagate through here, the contamination delay, right? So then I actually have a more stringent requirement on my hold time. The hold time cannot be too long. Okay. And similarly for negative clock skew. And then we also have clock jitter. The only difference between jitter and clock skew in your analysis is that jitter is a random variable. It can be positive or negative, equivalent to positive or negative skew. And you always look for the worst case in your formula. And then you can treat it as a skew. How about let's do an example, right? It looks complicated at the beginning, but you need to slow down. So first of all, right? Understand how it operates. What is this? Latch. Okay. It's not register, it's a latch. So the input comes in, right? And then we have a latch clock. It's going to copy the data from here to here. And then you have combinational logic. And then, when are you going to copy this guy to this guy?
Negative.
Only when it is negative pulse, right? So the question here is, it tells you that, hey, this one set up 2 nanoseconds before this clock comes in. Okay, 2 nanoseconds before the clock comes in. Okay.
For the falling edge of the clock, right? This is not just
Before the falling edge of the clock. So what does it mean? Because this one, when you fall down, then this one will be off, right? So that's why what you see is before it's off, it is already ready there for 2 nanoseconds. Okay. So why this is important? Because if you look at here, setup time is 1 nanosecond, D to Q is 1 nanosecond. So when this one was 2 nanoseconds before ready, then it means I already fulfilled setup time. I also passed it to the Q already. So at this point, I already have the Q valid. Correct? Right, so the question is, what is the maximum and positive and negative skew that is allowed for this clock? So I will try to draw it. First of all, let's look at the maybe negative skew. I mean, you need to understand why it's a problem. What is negative? What's the problem of negative skew? It means this one arrived earlier than this one. So what is the problem of this guy? If it arrived really, really early, what happened? Huh?
Hold time violation.
Can you speak louder? Data will not be stable or is not ready yet. If this one comes earlier, right? So let's look at this clock, right? If I have a negative skew, it will be something like this. Right? So you really need to draw the clock to understand. This is the negative skew. Correct? So here, the data is here, right? And then you have a negative skew, which is the same as this one. Actually, I probably should draw here. Right? This is also the negative skew. Right? It just shifts to here. And if you skew too much, then how much time do you have for this one to propagate to here? You only have this amount of time. So I actually draw the negative skew wrong. This is the negative skew. This one, from here to here, this is the negative skew. Do you agree? Right? And this one, I need to copy this data when this is low. But if I keep skewing to here, what happens? Then the high will be here. I cannot copy any data. I only have the time from here to copy the data. Correct? So this one equal to what? What is this one? What is this one? This is T divided by 2, right? So this one is T divided by 2 minus delta, right? Or, yeah, delta, let's call it negative, minus the negative skew. But this one is positive number, okay? For example, you skew by 5 nanoseconds, then it's T divided by 2 minus 5. You only have this time in order to process it. And what do you need during this time? you need the data to go through this one. And also to be ready to process. And then we can process it, we can copy it, right? So it means this one has to be larger than what? T delay logic, right? Plus T setup. Right, so as a result here, it says that the clock is 20 nanoseconds. So your delta, the negative skew has to be smaller than 20 divided by 2 minus 7 minus 1, which is 2 nanoseconds. Do you get this part? Actually, it's not easy, yeah. Contamination delay is the best case delay. The fastest time it can propagate from here to here. Because for logic, you have different inputs. Some input propagates very fast, right? That's called contamination delay. Okay, this is a very important concept you have to understand. Right? Usually, you only care about worst case delay, but contamination delay is very important also. Any question about this part?
So the speed logic setup time corresponds to the T period, right? Time period greater than
The period that you go from here and then stay for T setup so that you can copy, right? And this one you only can do within this low period because the data is only valid here. So I only have this much of time to copy.
But that data say they are telling about for the clock, right? So the in is valid 2 nanoseconds before the falling edge of clock, right?
This is it 2 nanoseconds before the falling edge of the clock, just because we assume that it's 2 nanoseconds ready here, but then it takes 2 nanoseconds to be ready here. Because you need setup time, you go to 1 nanosecond, and then propagation delay, you go to 1 nanosecond. So after 2 nanoseconds, which is here, this guy is ready. Then we only have to deal with this guy. Okay.
Professor, how is T by 2? Like, how did we find that it's equidistant? Like that?
No, we assume the period is T, so half of them will be T by 2. We assume they are symmetric. Duty cycle is 50%. This is D by 2, this is T by 2. We assume it is 50% duty cycle. Right, so it's not necessary. This one is 2 nanoseconds ready before that. Okay, remember this. It's not necessary. Then you have to recalculate. In this particular case, we say 2 nanoseconds before it is ready. That's why you can just ignore the propagation delay for this one. So in order to calculate this negative and positive skew, all you actually need to know how it is going to affect your circuit, right? For negative skew, you can see that, oh, this one come earlier, then I have less time to process it. Then I have to see if I can transmit the signal to here before I stop processing, before it is transparent low. Before this is transparent low, before this become high. Then it will become a block, right? Then you cannot copy data from here to here. It's just like a gate, you are the, what do you call it, the guard, right? You are the guard of a building, door 1 and door 2. Now the point is you need to let, maybe not the guard, maybe you are actually trying to steal something. No, let's say something good. You're trying to save people from here, right? So you need to control the gate, right? And when that guy open the gate so the victim can come out, you cannot open too early because you're going to close it immediately. This is a negative skew. So you have to make sure the victim can go through all this path and then arrive your place before you close the gate again, right? So that's what it means. So at this point, The previous guy said that, hey, I successfully rescued the victim to this door, and now they are running to you, right? But because of something wrong in your system, you actually have negative skew. You're trying to open it too early, and you are going to close it. But you cannot be too early. If you're too early, then when they run all the way to here, and then you already go up, the clock go up, you close it, the victim cannot leave. Right? At least you need to have this period divided by 2 minus this skew to be larger than the delay here. So that when they, at least when they run to here, at this point, you are just closing the door. They can pass the door. Okay? Question?
So the whole time is 0 here, right? Is it a good design?
No, whole time is 0 is good. Whole time is a requirement of your circuit.
Yes.
Well, if it's 0, it means actually it gives you more freedom to design the circuit.
Okay.
Yeah. And this is given in this case. Question just now? This is a negative latch, transparent low. Yeah. So when the clock is low, then the data can go through. That's why we want to keep it low until the data reach here. We don't want to go too high, too early, then the data cannot go through. Then your operation fails. Okay. Now we will go to the positive skew. Yeah, good, good. Yeah, almost, you are right. So now, if no question, let's go to the positive skew. Now the positive skew is saying that this guy actually go slower, right? So we need to redraw the diagram. So I'm going to draw here. We have positive skew, so you go up like this. Right, this is C clock, positive skew. Right. So what is the problem of this positive skew? The problem is that now, if the data comes in, good, I let it go. But what if I suddenly go up again? I go up, and then I have new data coming in. Then it's going to contaminate my data. It is this region giving you trouble. Correct? At this region, this is low, C clock is low. So this is transparent. But clock is high. So this is also transparent. I am copying the data to here, from here to here, and now you're copying another data. Now let's go back to our scenario. There may be some bad guy chasing the victim. The victim arrived here already. But man, you have positive skew. This guy also let the bad guy come out. And the bad guy is running so fast, right? You want the bad guy, you want the overlap to be so small that this one is not going to catch the victim. Once this one go up, I close the gate. He cannot catch the victim. Or the what? Yeah. Do you get it? So what does it mean? I want the positive skew, delta positive, to be smaller than the delay, the contamination delay from here to here, and then from here to here. Okay? So it will be T dq plus T contamination delay of logic. So here I only put TDQ because TDQ we did not give you contamination delay. So you can assume it is the same. You just have the same delay for worst case and contamination. The best case and worst case are the same. Okay? So This means that this one has to be smaller than 1 nanosecond plus 1 nanosecond. Right? So it has 2 nanosecond maximum positive skew. Yeah, pretty confusing, I know. But think about it. So the most important thing whenever you solve this is to understand the question quickly. You know, in all the exam, you already know that it doesn't require you a lot of work, right? It requires you to understand the situation, the background correctly. Once you understand what you need to do, you will be very fast to solve it. So same for cases like this. Understand what the circuit is doing, draw the timing diagram, right? Draw a field, play with that. Then eventually you figure out that for positive skew, I care about this. For negative skew, I care about this. Then you can write down the equation easily. Okay. Any questions? If not, then let me move forward, and then we are going to review some of the old stuff. But because of time, I will just fly over. Right? We know about how you define the VOH, VOL, VM, right? VRH, VRL. Assume you know that already, right? So this equation again is important. From this class, if there's one device equation you want to remember, it is this one. Okay. So remember this unified model. And then how do you find the minimum of VGT, VDS, VDZ? VDZ usually is given. Right? And we learn about the capacitance, right? I won't go into detail, but that's how you calculate the capacitance, right? So always remember when you see this one, there's a capacitance. It's due to the drain capacitance of the transistor, the wire capacitance, and the gate capacitance of the next stage, right? Lambda LC model, right? This is one of the most important things that we have learned. How to use Elmore delay to find the delay, right? So make sure you understand the procedure. I'm going to show you quickly. For example, how I find the delay from R to I, from here to I. I will just write down all the capacitor, C1, C2, C3, C4, Ci. And then find the common path between R to 1 and R to I. Okay? The common path is R1. The common path between R to I and R to 2. What is the common path? Only R1. Okay, very important. So we only put R1 for C2. The common path between R to I and R to 4. What is the common path? R1 plus R2, right? This is the common path, right? Let's just take a look. From R to I and R to 4. Only these two are the common path, right? This is not common to them. This is not common to them. That's why I put R1 plus R3 into C4. Okay? Do every node, including Ci. Okay? And this one is related. How do we find the transfer characteristic? We just equate the current, just like what we do in SRAM, right? You know this already. You learned this. You did that in the assignment too, right? And that's how we find the switching threshold. And yeah. And how to size the inverter? We already mentioned. Okay. So I will skip. CMOS property, they are actually simple to you. But for complex gate logic, you need to know the logical effort. I did not cover it, right? But we already tested in the second midterm. You want to learn them also. And yeah, I will just give p-value, logical effort, minimum delay, branching effort. That's just the same. Understand dynamic logic, how it works, right? All these problems, how to do the sizing, and then adder. I think you guys are better than me now after the project, right? You really look into the details, right? No kidding. I mean, just on, yeah. So I think I'll just stop here. Okay.
What kind of question you can think about? questions we can think of, like, or like multiple implementation with the adder? What kind of things we can do?
Good to say.
Okay.
Yeah, just study. Study the review. If you don't have time, review is very important. Okay. Yeah. Yeah. Oh, sorry. Let me stop the recording first.